All right, in this exercise, or this assignment I should say, we're going to look at automobile velocity control and design a PI controller for it. In the previous assignment, we did P-only control, which works well for integrating processes. For processes like automobile control, though, they're not integrating. What that means is if we take our foot off the gas pedal, the car will slow down. It won't stay at its current speed. And so what proportional control would do was as we approach toward, I'll just get out the pen. This is our box. Get out the pen. There we go. If this is our set point, as we were to approach the set point, the error is going to diminish, and because our u is only proportional to some error, so p times proportion times some error, the gas pedal will be let off until we reach some steady state below our set point. So what we do with proportional integral control is we look at all this area and we say we're going to penalize it as well, so that we start bringing this up and we minimize that distance until we are right on that set point. So proportional control achieves a faster response for bigger error. Integral control then minimizes persistent offset that can occur. All right, so we're going to look at this. We're able to do regenerative braking, which is where we actually set the gas pedal to -50 to 100 on this car. But our car model is very similar to what we had before. We're just going to do a momentum balance, which is basically a force balance. And that momentum balance takes the form that we've seen before. dv dt is equal to the quantity Fp times U minus 1/2 rho AC Vt squared, all divided by m. And so if we think about what the contributions are real quick, dang it, wrong thing for my pen. It always defaults to the box. I want it to default to this pen. This right here is acceleration from gas. And this is decel, force in the negative direction. And that's from resistance, especially wind resistance. So let's go ahead. What we're first going to do is we're going to design a control system. So let's just think through our control system for a bit and how the flow of information would work. We've done some block diagrams now, so let's go ahead and just do one more real quick. I'll get out my pen. I put it away on accident. So we have some set point. We're going to compare that with the actual sensor. So this is going to be velocity. So right here, the controller set point is the desired speed right here. From the set point, we get some error, E, which then goes to our PI controller. From the PI controller, we receive the setting, which will be right here, the actuator setting, OP, which is that pedal setting. That then goes, I'll just say P for process, it goes to the engine. That pedal setting then changes how much gas is going into the engine or how much electricity. And from that, we have our new velocity. So our measurement, our sensor is happening right here, where we measure what's going on, and the disturbances or variables are going to be things that are not part of this system that affect us. It could be more wind, it could be hills, it could be a change in cargo. If you have a crate and it falls off the back, all of a sudden that's going to be a disturbance because now it takes less energy to move forward. Our balance is different, our denominator in our balance is different. So I think these variables are very helpful to think through as you think through any control system. What is your actuator? What are you manipulating? What are you trying to actually control toward? What is your sensor that you're using to measure? And then what disturbances are around that may affect your system that aren't explicitly controlled? So the first thing we want to do is we want to fit a first order plus dead time model. And with that, we can come up with initial tuning constants for this system. I'll go ahead, I'm just going to close out some of the tabs that I already have. And so what we'll do is we'll have a final time at 60 seconds, and we'll say we're going to go for 61 seconds. Our delta t then will be time final divided by number of steps minus 1, so that will be, delta t will be 1 second per time step. And then our ts is going to be a lin space from 0 to the final time with the number of steps we're having. This is just so that we can do that automatically. We could also write in, for example, 60 here and 61 right there. Then we'll have a step test where we'll have zeros as our step initially, and then at element 11 till the end, we'll set our valve, or not our valve, our valve, a gas valve, to 50%. We'll set the passengers as the load for passengers and cargo to 200 kilograms, and our velocity initial condition will be 0. Our set point will be 25. And then we'll go ahead and store our results as far as the set points and the velocity simulated. And we'll go ahead and look at that. What we'll do is we'll have this framework so that we can go ahead and use this as well, similarly in our actual simulation with a controller. So let's look at our results from this simulation. You'll see that our set point is supposed to be 25 meters per second. But we're actually going up. And I don't know that we ever fully hit a maximum velocity. Let's say that our maximum velocity is about 45. It's where it's fully reached steady state. Well, let's use our command window really quick, and let's start regressing our variables. And actually, we can do that down here. The first thing we need to do is we need to regress these parameters, kp, tau p, and theta p, and from those, we'll get our controller parameters kc and tau I. So this is the gain of the controller now, and then the derivative time constant. And we'll get those from our tuning correlations, which we briefly talk about within our lesson. So our dy, we start at 0, we say we go to 45, so we'll say 45. Our du is 50. Our kp is going to be dy divided by du. Our theta p is the time it takes from 10 seconds to reach 63% of the way there. Well, let's see, 63% of 45. What's 45% of 63? 50% is like 32. And then 5% of that is going to be, say 30. We'll say it's 30. So it reaches 30 right at about, let's say 28. So it's 18 seconds is what our guess is. And our tau p, it looks like 1. It's pretty instantaneous that it at least starts. So what we want to do is we want to use those correlations to help us find what our kc and our tau I should be. Here we have what kc should be. It should be 1 over kp. And I want to move this actually. I like this. I knew it was down here. I was thinking about that while I was talking. I think it's better to regress these out in front so we can see. I realize also these are flipped, which could cause some problems. Theta is the dead time, and that's about like 1 to 2 seconds, if any. Tau p is the one that we're going to say is 18 seconds. So first, if we go to our, here we are in lesson 12. If we go to the lesson, here we talk about proportional integral control. Hopefully you did that. You did the lesson before you're doing the assignment. That's interesting. Let me try opening it again. There we go. So let's see if we have our tuning correlations, and we do. So we have rough simple coordinate correlations that say that Kc is equal to 1 over Kp, and tau I is equal to tau P. So let's go ahead and let's just write those out. We have the one that we copied, which is Kc is equal to 1 over Kp, and tau I is equal to tau P. We'll do semicolons. Perfect. Then we're doing something similar. We have a final time of 5 minutes, 301 points between those, and we're going to do a step for each one with our linspace counting up. We will initialize the load to 200. Our initial velocity is 0. And then we have our simulated velocity. We have our, and these are all vectors to store our results. So simulated velocity, our storage of the U setting. You can see I accidentally made it run already, but we'll look at it in just a second. Our set point, in fact, we'll go ahead and we'll just clear all output because we still need to type some things in. So our set point, our error, and our discrete integral here. And then for I from 1 to divide, we're going to go ahead and basically what we're doing here is we're setting the set point in random integral and in random chunks of 50 seconds. We're going to set the set point somewhere between 0 and 40 is what's going on right here. So we come up with some random set points so that we have changes in set points. Then we're going to take for I and 1 to n steps minus 1, because the last step we don't need to calculate the future step. Our error is going to be sp I minus our actual value, which is going to be vsim I. Our error then is going to be stored in error I. Our discrete integral of error is going to be equal to itself, so go ahead and copy that, discrete int plus error times dt. So for each value it's going to add the error times dt, and that's kind of like a just the discrete sum over that last time step, and we're adding that to the previous value. Finally, we have u. Let's think back to our PI controller equation now. In fact, let's look at it. U is equal to U bias plus Kc times Et, which is the error, plus Kc divided by tau I times the integral of error. So our U bias is 0, so we'll just leave that out in this case. So we have Kc times error plus Kc divided by tau I. Let's see, how did I spell that? Tau I with capital I. That's how we usually do it. Times disc int. And that's our PI controller. It will set our U, and here we're making sure that the maximum is 50 or 100, and the minimum is negative 50. So we're able to break. And then we integrate from the 1 second to the next second using this vehicle model. This vehicle model is just the differential equation that will integrate with ODE 45 using the constants and then doing the physics-based force balance. We'll go ahead now. Let's go ahead and plot our results and see how well our PI controller does. So you can see we have a little bit of overshoot here. We overshoot the set point here shown in red, and then we need to get down and something similar happens and we get down right here. So to do that, let's maybe set our tau. So what's going to affect this? The overshoot is generally caused by one of two things. It's either caused by the integral of absolute error, making it so we need to so we have this integral of error underneath, and so we need to overshoot it until we get right back down. Basically, we need to match the area underneath and up top until they are equal is one problem that happens sometimes. And so to do that, what we can do is maybe just make our integral control a little bit more conservative. To do that, we'll take our tau p and we'll just assume that it's a little bit longer. So let's say it's equal to 22. Remember, because it's on the denominator, higher values are more conservative. So we'll go ahead and write it again. Just look at what the difference would be. So here we have a different set point, so it's going to perform a little bit differently. But this one, I like how it performs. There's a little bit of overshoot here, but other than that, it reaches the set point of 30 pretty well. We'll look at how we make these controllers better in a future course or in a future lesson where we talk about tuning these controllers. Right now we want to focus on just the principles here, which are that the proportional integral controller is dependent on some proportion of error plus some proportion that depends on the integral of error. And the whole point there is that we get rid of persistent offset that occurs when we only have the proportional control. Thanks for watching. Let me know if you have any questions.